So we do a lot of, not as much as we collaborate with UK and Dr. Williams, and but we do kind of have small plots that we grow hemp and for our own work. In terms of we don't do grain, but we do mostly fiber. But we work with our biology department and other types of other groups there. We collaborate quite a bit with other universities as well, and grow different types of biomasses, and we convert them into value-added products. So one of the things that our approach essentially is that this is the model we use. When look at petroleum, and when you look at the 1 barrel of petroleum, crude oil, we have different products we get out of it. Gasoline to diesel fuels, liquefied petroleum, jet fuel, asphalt. So there is bottom line is there is nothing that's wasted out here. Every drop of crude oil that we get in, we use it. Similar approach we need to have for the biomass types as well. That means we need to maximize the net value and minimize any other waste that's generated. So from that point of view, if we look at some of the hemp biomass, because whether you're growing for grain, whether you're growing for fiber or CBD, you will have biomass. And how can we maximize the value of it such a way that that there is some economics out there to the farmers, and we have more biomass feedstock for bioproducts. If we look at the composition of hemp stalks, essentially what we have is you have two, you have hemp fibers and hemp stripes, which is hard. And ash content is kind of in the stripes, it's kind of low. On the outside, on the fiber, there is more ash content. But look at the cellulose value, they are mostly cellulosic fibers. And the hemicellulose value is low, and lignin is low. And on the other hand, the core, the hard stalk inside, you still have cellulose inside that, and they are not as long fibers as the cellulose is. There is something called degree of polymerization. These are long, DP cellulose fibers. But you have more hemicellulose here and more lignin content. So that means with this composition, how can we kind of engineer the process such a way that instead of not finding a value for it, how can we make sure that we find a value for it? So that's the opportunity we're looking at. So the opportunities I would like to share with you are some of the products that we are working using hemp stalks. One is a low-calorie sugar called Xylose we make from these hemp bio stalks. The Xylose is about $1.70 a pound type of low-calorie sugar. I'll talk more about the sugar. And then obviously the bast fiber that we are using, similar to what Sunstan is using. We use a different process, but we get natural fiber composites. We have doing a lot of work on that. We're using it based on the process that we put in. We can go after very high surface area carbons. Again, from energy point of view, energy storage, batteries and all that, lithium sulfur batteries, they need high surface area carbons. We produce them using the herd. And then any of the remaining biomass waste, we're using them for pelletizing, for white pellets, also as torrefied pellets, because bio-derived coal is a drop-in replacement for coal, and it has no sulfur emissions, no NOx emissions, and it's a carbon neutral coal. It can pound per pound, it can replace coal. It can supplement coal, it can go along with the coal, so that will be something that the coal industry can use as well. So these are the products that we've been working on. I would like to share with you some of the work we are doing on this. The majority of the time when we are taking the fiber out, we are doing something called mechanical decodification. Because the dry process, fairly low capital intensive process, and when you draw comparisons to paper making pulp, you can make mechanical pulp, newsprint pulp, which is kind of fairly low, and high yield pulp you can make it, low quality. And you can make high quality pulp, going all the way to paper grade pulp, all the way to dissolving grade pulp, going to tissues and high absorbance and all that. You can increase the value of the cellulose by choosing what kind of process that you put in. So the process that we have chosen is a selective hydrolysis process, which selectively take the C5 sugars out. The hemicellulose is a C5 sugar. And once you take the C5 sugar out, we're able to get the fiber out hard and as a very clean stock, and we also get something called a C5 hydrolysate. So this is the path we have chosen based on the other work that we have been doing at Conn Center. I'll explain to you our rationale behind why we are choosing this process. Again, fiber, as a high quality fiber that's coming out, our objective is to put it in, we have so much automotive industry, auto parts industry, that 3D printing and making them into the composites and making them into strands for the 3D printing is one opportunity we're looking at. Because the long fiber with the high cellulose content, we can modify it to whichever end use we can use, because we can put the polymer is a hydrophobic material, cellulose is hydrophilic, so we need to match the interface between the polymer and the fiber, so we can modify the fiber such a way that we minimize that's one of the technical challenges, that we minimize the resistance at the interface so that we make a very nice filament comprising of a high, some level of fiber and the polymer, replacing the polymer, and then we go into 3D printing. We know that for 3D printing, what kind of different things we can do. And the challenges are essentially, fiber dispersion. How do we make sure that in a polymer material, the natural fiber is dispersed properly, and the fiber retting process that we have chosen gives us more opportunities in terms of the removing the anisotropy. We need to make sure that isotropy is there. The properties are machine direction as well as cost reduction, well, uniform properties. We minimize the anisotropy using some of these modifications we are doing. So with the 3D printing for the auto parts, automotive components, even the structural components, we can kind of do more opportunities with the way we're making the natural fiber, high pure fiber that we can modify to different qualities. And 3D printing is one opportunity that we are looking at. We have been working with our mechanical group. We have a additives manufacturing facility at the University of Louisville. We work with the manufacturing industry quite a bit, all the automotive manufacturers as well as aerospace manufacturers. And 3D printing is becoming, with natural fiber, sustainable manufacturing is something that customers are looking for. And this is one area we're putting our hemp fibers in. And the other opportunity, again our interest in 3D printing is that this is going to be a $5 billion industry. When you look at, he has shown his shoes, Nikes versus automotives, so everything is going to be eventually 3D printed. With auto parts, everything, custom-made auto parts and all the stuff, Tesla is a 3D printed material. And then you can clearly see that, 3D printing, natural fibers going to 3D printing opportunities. It's a modular process that we can put in. Even the fibers coming from, somebody was asking the question whether we can use the one from CBD biomass or not. This is one opportunity that we can put all kinds of fibers into the 3D printing opportunities. So this is one area we are working with. The second area is the herd. The way we are doing the selective hydrolysis is, you have seen the composition that herd has very high level of ash. When you have ash, ash is basically going to lead to impurity in the carbons. The acid process that we use removes the ash. And we remove the ash, make it low ash starting material for carbons. And by the way we make the process, if we don't go through our process and make make carbons, activated carbons, we get at the most 100 square meters per gram surface area. But the moment we go through our process, we remove hemicellulose and all that stuff, we get up to 1200 square meters per gram. The electric storage capacity is directly proportional to the surface area. So high surface area means you can store them. Now all of a sudden you are increasing the value of carbon from 50 cents a pound to $14 a pound type of opportunity. So humongous opportunity is there by integrating the process and putting the right process together. And with these herds, we are essentially going through activation carbonation process, and we make very high surface area carbons. You can clearly see that the porosity and the surface area are increasing quite a bit, and we have done a lot of testing with these materials into lithium batteries and supercapacitors, photovoltaic cells, and even for hydrogen storage. We were able to use them, and they're working. They're showing very good promise in those areas, and we're also putting them further into these carbon-based catalyst supports. Because of the poor volume we have, we can basically put nickel, platinum catalyst inside these things. These become very carbon support, sustainable carbon supports for catalysts. So we've been using, we are having very high success with the herd material going into carbons and catalyst supports. The other area that we have doing is, I mentioned to you about biocoal opportunity, and we have on campus, University of Louisville campus, we're doing quite a bit of work on the biocoal. We have a pilot plant essentially that makes about 300 pounds an hour type of opportunity. We're working with different types of biomasses, wood coming from California forest, Oregon forest, the one that is currently being burned. And we're working with bagasse, we're working with hemps and canaps and all those stalks and all that. Objective is to make them into a densified biomass, densified drop-in solid fuel. Pellets, as well as briquettes, torrefied as well as non-torrefied. And when you go to Europe essentially the household heatings and all that, everything is happening with waste wood. And they sell them in the retail market. So, and when you go to Maine, white pellets are for household heating, they have been using wood white pellets as well. So hemp can be one of the opportunities. We are working with some of the hemp and canal producers into making pellets. And we have, as I said, we work with different types of biomasses, made several tons of these materials on a regular basis. The key to making these torrefied solid fuel, drop-in fuel, is that the test over there in the corner. This one here. The biomass is hydrophilic. It cannot, when you densify it, it cannot withstand water. It cannot be stored outside. Whereas coal in a power plant is stored outside and it has to be a drop-in replacement for coal. That means it has to be very hydrophobic, very strong. It should not be any dusty. And that's the kind of product we made. Even after 48 hours, the densified coal, essentially made from biomass, stays intact. Doesn't even absorb any water. So that's the kind of product we are making. Not only that, it should be grindable, and it should be a drop-in replacement for coal. And we're able to we have a patent pending on this. We're able to make this kind of product from using the various types of biomasses, and including we are getting strong interest on the hemp and canaps to go into pellets and briquettes. The next product I would like to share with you is the sugar, xylose sugar. This is a low-calorie sugar, and it's essentially a zero-calorie sugar. The true natural sugar out there is something called Truvia that they sell currently, made from the Mexico Xavier plant. And that's the only true natural sugar out there. And xylose is, next to glucose, that's the most abundantly naturally available sugar in nature. And most of the time, it is wasted because of the way we process the material, process the biomass. We focused on pre-processing techniques such a way that we recover xylose as a product. Yeah, as I said, this is about $1.70 a pound, and currently it's used to make xylitol, which is a polyol, which is modified sugar. But xylose as a sugar itself is fairly doesn't metabolize in the body, and obesity-wise, diabetes-wise, is kind of fairly shown to be very effective. And it's as I said, it's kind of used as xylitol, but we are trying to kind of use this as for the food and consumer applications, as well as our objective is essentially to get this sugar, which is a xylose sugar, a C5 a 5-carbon sugar. We essentially using synthetic chemical techniques. We are converting that to a tetrahydroxypyranone, and once this as a platform chemical, we're going after plastics, we're going after jet fuels, we're also going after 3-THPs and all that. So different types of the platform chemical, we're trying to kind of put that into biofuels application. The way we do that is, let me go back. We have a patented process that we take the hydrolysate that's coming from the retting process, and we have under ambient conditions, we developed a patent such that we capture the sugar in a solid form and precipitate it. That's our patent, and we use we form a diester of the sugar with a chemical, and drop the chemical out. That means remove all the water out, and then we recycle the chemical back and kind of put the pure sugar out. That's about 99.9% pure xylose. It's going through piloting stage at this point, and we gave samples to major users like DuPonts and Dows and Cargills, and they tested the product, and it meets their specifications as well. So that's the kind of sugar opportunity we're looking at. So overall, what we think is we can maximize, similar to what petroleum industry is doing with their crude oil. We should maximize what are the biomasses coming out from hemp. We showed that we can use them into various multiple opportunities. That's the integrated biorefinery concept that we've been trying to commercialize. Stalks through chemical retting process, going through, we are making a pure bast fiber that can go into composites and coarse stock into various opportunities, and hydrolysate going to C5 and xylose, and then the carbons going into various applications. These are the kind of different type of product portfolio we're trying to put from bast fiber crops such as hemp and cannabis. That's all I have. Any questions?
Yes, question.
Okay, when you're taking the process and you're using different processes on different parts of the plant, right? So how much waste did you wind up with?
We utilize everything. When you go to the carbonization process, there is no waste.
No waste at all.
See, the biomass coming in, that's where the logistics, someone was asking about the biomass. Biomass as a starting material is a low dense, it's a low density and bulk. So logistics wise, and we need to make sure that the processes are modular. That's what we're trying to do here. It's a modular process. Whatever starting material is coming in is fully utilized, and we don't generate any waste. Going through the carbonization process, at the most it converts into water vapor and carbon dioxide. We make sure it's in that condition. Hopefully not carbon dioxide, but it's that as heat and steam. Those are the waste coming out, but everything else is converted into a bioproduct. We put the pro formas on this, and the paybacks on this process are about within 2 years. You can have a nice paybacks on these processes. We are in the process, in the mode of commercializing some of these opportunities. Yes, sir.
So what are the uses, like, are they going to use the filament for the 3D printing, like, what's primary?
Well, with 3D printing, the opportunity is when we say natural fiber composites. When you look at the density of polymer versus the density of fiber is supposed to be lighter. When you have pound per volume replacement, essentially, When you replace the polymer with fiber, you are making a lightweight composite. And then when you when you make a composite like that, you have two options. One is a molding opportunity you can go into, or a 3D printing filament, 3D printing opportunity. 3D printing wise, you can really control how fine how fine a filament you can make, how thin a composite you can make, and still maintain the strength. That's the beauty of 3D printing. That volume, you need to fill the volume, but if you make a lightweight material, you can still make the composite whole end product lightweight. So that's where the opportunity is. That's where you can kind of cut down the polymer, make it lightweight, improve the gas mileage, and so that's how you are making the impact on the environment, on the greenhouse gas. Yes, ma'am.
So have you worked out, say, tonnage-wise, what the value that you can pull out of, say, a ton of hemp fiber, of the plant as it comes out of the field, from the bale?
Yes, I come from manufacturing background, and we work on something called net raw material cost.
Right.
We need to make sure that net manufacturing cost, net raw material cost is as negative as possible. And that's how we kind of, when you look at when you draw a black box around the fiber, look at all the products coming out, look at the value of it, look at the value of the fiber itself, that should be negative. That's how we design these products and processes. It is, when the payback is within 2 years, it is, the products are making more value than the raw material.
Well, let's thank Dr. Nod very much.